All right, let's recap what we did last time. Last time we showed if V is a Lyapunov function for 7.11, then the zero solution is stable. Lyapunov function means V0 is zero, Vx is positive, V prime is less or equal to zero. And then if this inequality is strict, then we have asymptotic stability. Okay? Now, we did a couple examples, and for this problem here, minus y plus xy, y prime is x minus x squared, and if we do ax squared plus by squared, ab is positive, we have v0, 0, vxy is positive, and we would like to see what happened. So we take v prime and we get that. And then if I take a equal b equal 1/2 or a equal b, then minus 2xy plus 2xy cancel out. 2ax squared y minus 2x squared y minus 2x squared y equals 0. So 0, 0 is the center. And here we notice linearization does not apply because it will give you a center. Okay. Now, let's take a look at this example here. I got excited yesterday and I gave you a little bit of misinformation. I saw this was the example we did. It was the other one on the other board I showed you. So if I take v equal x squared plus y squared, then there we go. Then v prime is 2x minus xy plus 2y minus y x squared. And that is minus 2x squared minus 2x squared y minus 2y squared minus 2y squared x squared. Minus xy squared. There. All right. So as you see, this is less than 0 because if you factor, this is minus of x squared plus y squared. All right. Minus 2x squared y squared. There we go. Plus. Okay. So in other words, this should give us minus 4. This should give us minus 2 of x plus y squared. There you go. So what's less than 0? So that means 0, 0 is asymptotically stable. And then we took this Lyapunov function not necessarily. Well, you see, you're saying if it is equal to 0, the loop may not be. For example, here in the previous examples, well, stable means that it's going to be a center. The point is going to be a center. So yes, it formed a kind of a loop around the equilibrium point, but only if v prime is 0, correct? Only if the derivative is 0. Like here, if the derivative is 0, then if the derivative is 0 and then you will we have dv over dt is 0, that means v is constant. But what is v? x squared plus y squared equal constant, that is a circle. So it's a closed loop around the origin, only if it is 0. Here, it is less than 0, asymptotically stable. The solution could spiral toward the origin. Okay. Okay. So now I can take another Lyapunov function, and we saw yesterday this gave us less than 0. So either Lyapunov function gave us the same stability. All right? All right. So this is from yesterday. Now, I want to go back to exercise 5.4. So we have x prime is minus 1 plus t e to the minus t, 2 plus 1 over 1 plus t squared, 2 plus e to the minus t, minus 4 plus 1 plus t, minus 3/2 x1, x2. All right. So it's not a theorem I used. So this, we're going to change this to minus 3.5. It's not something I use. So I'm going to write this x prime equal to minus 1, 2, 2 minus 4, x1, x2, plus t e to the minus t, e to the minus t, 1 over 1 plus t squared, and 1 plus t minus 3.5 times x1, x2. All right. So you can prove a theorem. So let's take x prime equal ax plus btx. So let's prove a theorem. So what are the eigenvalues here? So you can use a theorem. So we're going to use theorem 5.14a. Theorem 5.14a. So take a look at it. So we have e to the at is less or equal to d. Why? Because the eigenvalues of a are, I did this morning, are 0 and minus 5. So that means by theorem 5.41 e to the at is less or equal to d. So then what is the solution x of t? X of t equal e to the a. Let's assume we have x0 equals 0. Equal e to the at x0 plus t0 to t e to the a t minus s b of s x of s ds. This is what it is. So this is B. This is the matrix B. So you really need to prove this theorem. So then x is less or equal d x naught plus, oh, I'm talking about 0 here, so let's take it 0, plus 0 to t, this is d, correct? E to the at minus s, still be some constant times bs x of s ds. Okay? This may not be the same constant, but it's I mean, whatever you want to call it, really. Let's call it k. Okay? All right? So now use Gromwall's inequality. Less or equal to dx naught e to the k 0 to t bs ds less or equal to dx naught times e to the k 0 to infinity bs ds. Now this is less or equal to dx naught e to the k e. So where we assumed and then you get a stability from here, guys. Okay? You get a stability. All right? So you see how you're supposed to do it? So it's like a hidden theorem. All right. Any question about that?
I think that's pretty much just theorem 521, which I don't think we covered in class, but it is in the book, if I'm following.
5.21 in our book?
Correct.
Oh, yeah, this is when you do similar matrices. Okay? Well, I want you to do it in a sense that I mean, I want to be a little bit creative. Okay? All right. So, or you can prove the theorem. All right? Yeah. It's similar to it, but it's not the exact one. All right. Any other questions? Okay. Quick understanding question. A Lyapunov function, if it exists, need to form a closed loop. Oh, okay. We already answered that. Any questions? I do enjoy your questions. If you have some, throw them at me. All right. Uh, all right. Now we're going to go back to Lyapunov functions. I'll be with you in a second. Let me get my book in order. All right. Okay. So All right. We've done all the examples. Let me do one more example. All right. Let's take x prime is minus x y squared. Y prime is minus y plus 3x squared y. Okay. So let's take a look at v equal ax squared plus by squared. A, B are positive. Then, so here we have 0, 0 as a critical point. Then we have v0, 0 is 0. And v of xy is positive for xy different from 0, 0. All right. So we're gonna find a and b. 2ax minus xy squared plus 2by minus y plus 3x squared y. Okay. So if you look at it, this is 2a minus x squared minus 2b y squared minus 2ax squared y squared plus 6b x squared y squared. Okay, now I want these two terms to cancel out. So if I take a is 3 and b is 1, so this is gonna be minus 6x squared minus 2by squared. A equal to 3, that will be minus 6x squared y squared plus 6x squared y squared minus 2 y squared. That is minus 6x squared plus 2y squared is less than 0. And so 0, 0 is asymptotically stable. Okay, so there we go. Okay, now let's say I take v is ax plus by. A and B are positive too. Okay. So v prime is ax over x prime plus by over y prime. That is ax over x prime is minus xy squared plus by over y minus y plus 3x squared y. Okay. So that is minus ax squared over x times 1 plus y squared plus b y squared over y minus 1 plus 3x squared. All right. So this is minus ax times 1 plus y squared plus by 3x squared minus 1. Now, what do I really need to get rid of? I need to get rid of, so I would love to keep minus ax let's see, minus y. Okay, so let me go over it again. So I'm trying to give you different example. 1 plus y squared plus by 3x squared minus 1. Because I am factoring x squared out and simplifying by this. That will give me 1 plus y squared. That will give me plus minus 1 plus 3x squared. Okay, so we need, so I am in a good shape. This is minus ax and minus ax y squared plus 3b yx squared minus by. Well, you see, we are at a loss here. So it is very hard. So does not mean, so this is difficult to get rid of these terms. These two terms, difficult to get rid of. All right. So you see, one layup on a function may work, another one you may think it will work and it won't. So this really does not give us a good idea on how to proceed. Because I need to choose A and B, and A and B cannot be chosen in terms of X or Y. They have to be constants. Okay? All right. So that should clarify things. This is not in the book, by the way. Okay, now I'm going to talk about all right. Okay. suppose V is a strict Lyapunov function. Okay, then the domain of attraction of an equilibrium consists of all points such that a solution of them tends to the equilibrium. Okay, so this idea is this idea is important in engineering because they want to estimate the domain of attraction. So thus, definition, I did not state it as a definition. If V is a strict Lyapunov function, on a set D, including in Rn, then the origin is asymptotically stable, and the domain of attraction is n equal to all x in D, such that Vx less or equal to C for some positive constant C. Okay. Okay. All right, let me do an example. Go ahead and copy it down. Okay, so let's take an example to see how we do it. let's consider example 7.6. We have x prime equal to minus x minus y. Y prime is 2x minus y plus y cubed. Okay? So clearly, 0, 0 is an equilibrium solution. And I'm gonna take phi to be x squared plus y squared over 2. You can take ax squared plus by squared and accordingly choose a and b. So this is behind us now. You could do that. So basically, I am saying a is 1, b is 1/2. Then v prime is 2x minus y plus y, 2x minus y plus y cubed. Okay? So again, v0, 0 is 0, and vxy is positive for xy not 0, 0. This is a part of the definition of positive definiteness of the function v. All right. So this is minus 2x squared minus 2xy plus 2xy minus y squared plus y4. So these two go away. So this is minus 2x squared minus y squared plus y4. So this term is negative. Now this term, we want it to be negative. Want it to be negative. So minus y squared plus y4 is y squared minus 1 plus y squared is less than 0, or minus 1 less than y less than 1. Or for y less than 1. Okay? So v prime is less than 0 for all x not 0 and y less than 1. Okay? So let D be the set xy such that x in R and minus 1 less than y less than 1. And set v of xy equal to x squared plus y squared over 2 equal to c. So we want n bar to be all the set xy belong to D such that vxy less or equal to c less or equal to less than 1/2. Why less than 1/2? Less than 1/2 because this will always be, okay, xy is less or equal to c. This is less than 1/2. So that will guarantee that this one plus this one is always less than 1. Okay? So if I guarantee that, then this is my domain of attraction. So this is my domain of attraction. This is the set of, so it has to be less or equal to 1/2. Okay? So that will guarantee it, because I am saying if y is 0 and x is 1/4 or 1/2 or 1/square root of 2, this will always be less than 1/2 for all y in this domain. Remember what y is. Okay, so this is the domain of attraction. Okay, and remember the way we defined it here is v of x less than c, the domain of attraction for some positive constant c. Okay. All right. Any questions? All right. Because x can be 0, so this has to be very close to 1/2. So this is the worst case scenario. So there is a restriction on x in here too. So not only on y, because v give us a restriction on x at the same time. All right, any questions? All right. Let's say I'm going to answer somebody a question. Let's say we have x prime equal to x times y minus 1. Y prime is y x minus 1. So we got x equals 0, y equal 1. And y equals 0, x equal 1. So for x equals 0, if x equal 1, y equal 1, this is a critical point. So we have 1, 1. Correct? And we have 0, 0, 2. Okay? So the critical points are 0, 0, and 1, 1. Correct? How would you define this Lyapunov function for the other one? So what you're gonna do is we're gonna take v equal a times x minus 1 squared plus b times y minus 1 squared. First of all, v of 1, 1 is 0, and v of xy is positive for xy different from 1, 1. You see how you improvise? Okay. Yes, you need to find a critical, you need to find a Lyapunov function for each one of them. Well, I mean, let's do it. V prime is 2a times x minus 1 times x prime times x y minus 1 plus 2b times y minus 1 times y prime, which is y x minus 1. Well, good luck. Okay? And good luck computing this to see if you can get stability out of it. I'm just giving you an idea how to go about the Lyapunov function, okay? Or you shift your theorem, or you shift 1, 1 to 0, 0 by taking x bar equal to x minus 1, y bar is y minus 1. Then you will have x bar prime equal x prime equal to x equal x bar plus 1 times y minus 1 times y bar, and y by prime is y prime, and y prime is y, but y is y plus 1 times y minus 1 times x minus 1 times x bar. So now work with this one and you will see 0, 0. So now 1, 1 becomes 0, 0. So take v of x bar y bar equal a x bar squared plus by bar squared. Okay? You can do it either way. How's that? So you can go this way about it or do it the other way. All right. Any more questions? Okay. So that is for the, now we have a very important theorem. I'm going to skip the proof. Theorem 7.14. Okay. Let v of x be a Lyapunov function on a set D. Of course, D containing the origin. Okay. Let the Z be all x such that v prime of x equals 0 when x belong to D. Suppose that the only bounded solution um, stay with me, make sure I want to get this in. Um, $7.111. Just give me a second. Which remain inside Z inside Z for all time is the equilibrium solution zero, then the origin of 7.1.11 is asymptotically stable. Okay. The proof is beyond the scope. I mean, it's not beyond, but I'm not gonna do the proof. And we will see why. Instead, I want to do an example. Okay. All right. So let's do an example instead to illustrate the idea. This is example This is example 7.7. So we have x prime minus x minus 2y, y prime equal to 3x minus 2y. Okay. So let's take phi of x. So again, 0, 0 is an equilibrium solution. Okay. Because you solve for here, you put it here, you get x equals 0, then you get y equals 0. So 0, 0 is the only equilibrium solution. So let's take, so go ahead and compute the derivative. First of all, make sure this is a positive definite and compute the derivative and see what you get. So take a few minutes and so you do that. All right. So v prime is x prime plus 2y prime x minus 2y plus 2y 3x minus 2y, and that is minus x squared minus 2xy plus 6xy minus 4y squared, and that is let's see, what am I getting here? Oh yeah, that is minus x squared minus 2xy plus 6xy minus 4xy plus 4y squared, and that is minus x minus 2y squared. Okay? So notice that v prime equals 0 along x equal to y. Take a look here. V prime equal to that. So v prime is equal to 0 along x equal to y. Look at it. So this is your set z. So z is all the set x such that v prime all the set xy such that x equal to y. There we go. So this is your set z. Okay? And what is, okay, I can even do better. This is in R squared such that x equal to y. So this is the set v, z. Suppose the only bounded solution which is remain inside z for all time is the equilibrium solution. So that is a huge statement. Okay? Okay? Suppose that the only bounded solution which remain inside z for all time is the equilibrium solution. How's that? So, any question here? So we want let x be less or equal to k, y less or equal to k, be the required bounded solution. Bounded solution be the bounded solution that the theorem asks for. Now, for x equal to y, what is x prime? X prime is minus x minus 2 times x over 2. This is minus 2x, which have the solution xt equals c1 e to the minus 2t. You see that? same y prime is 3x. 3x will be 3 times 2y minus 2y. That is 4y. And the solution yt is c2 e to the 4t. Okay? Clear? Okay? Now, any questions? Okay, so let's continue. Now, we have y that's equal to k. That means c2 e to the 4t less or equal to k. This is only when c2 is 0. For all t bigger than 0, or as t goes to infinity. Remember, bounded. Then x equal to y, that means c1 e to the minus 2t equal to 0 as t goes to infinity. Okay? Or may I say x equal to y, that means c1 e to the minus 2t equals 0. This is if and only if c1 equals 0. So therefore, x equals 0, y equals 0 is the only bounded solution that remains in D. In Z is the only bounded solution and that remain in Z. However, 0, 0 is the equilibrium solution. That means xy goes to 0, 0, and 0, 0 is asymptotically stable. Okay? So this here, so here is a theorem that tells us V prime is not less than 0 to get asymptotic stability. V prime is equal 0 along some solution, along some trajectory. And here the trajectory was x equal to y. So we took x equal to y, put it back into the system, and solved for x and y, and then showed that x and y has to be 0 both if we want the bounded solution. Okay? Or you can argue that x of t equals c1 e to the minus 2t, yt equal to c2 e to the 4t. So along x equal to y, we have c1 e to the minus 2t equal to c2 e to the 4t for all t. But this is if and only if C1 equals C2 equals 0, then X equal Y equals 0. Okay? It's another way to look at it. What do you think? Any questions? All right. So let me talk about instability using Lyapunov function. Okay. So this is theorem 7. Let D be in Rn, 0 in D, and let V be from 0 to infinity cross D cross R into 0 infinity with V0 equals 0. V of X is bigger than 0 for X different from 0. And V prime of X is positive. Then the 0 solution of X prime equal F of X with F of 0 equals 0 is unstable. Okay? I'm not following the book. I just rewrote the theorem as a lecture note. All right? So take a look at it. Let's do an example. This is example 7.8. We get X prime equal to XY plus X cubed. Y prime is minus X squared plus Y5. So we got 0, 0 is the equilibrium point. If you use a linearization, so you calculate Jacobian, del f1 over del x will be 2y plus 3x squared. Del f1 del y will be 2x. Del f2 del x minus 2x 5y4. And if you look at the j of 0, 0, that is the zero matrix. Okay? So we got lambda equals 0, 0. So linearization, no information. Okay? No information when the eigenvalues are zeros. So linearization here fails, what I'm trying to say. Okay? So let's lay up on a function. Let vxy equal x squared plus 2y squared. Okay? You know, this should be suspicious, that because the solution x, any solution is going to have c1 plus c2t. And as t goes to infinity, this is going to go to infinity. But this is not an affirmative answer. You need to, the linearization says nothing. So v prime, of course, here, v0, 0 is 0, and vxy is positive for xy different from 0, 0. Okay? Now, v prime is 2x times x prime, 2xy plus x cubed plus 4y minus x squared plus y5. Okay? And this is 4x squared y plus 2x4 minus 4x squared y plus 4y6. Now you see 4x squared y could be negative, could be positive, but we're lucky it canceled with this. So that is 2x4 plus 4y6, which is this positive 4xy different from 0, 0. So the 0, 0 is unstable by theorem 7.1.5. Okay? So the zero solution is going to be unstable. Any questions? Any questions? All right. I am going to stop here and pick it up next time. And I will need maybe 2 days next week. That's all I need. We'll talk about it. If I need a 3, I need a 3. I'm going to assign a new homework today. That will be the last homework related to Lyapunov functions. Okay? You guys take care. And we'll see you later.